Feed project parameters into a model like Kokomo, and it outputs a precise baseline: 5 million rupees, 10 months, 8 developers. But when the project ships, reality hits. Cost reaches 8 million, the timeline stretches to 15 months, and the team swells to 12. The math in the initial calculation was perfect. The formulas were executed exactly as designed. Yet the real-world execution resulted in a catastrophic overrun. To bridge the gap between theoretical calculations and real-world friction, engineers implement a distinct phase called estimate validation. Estimate validation is the rigorous, systematic evaluation of projected cost, time, effort, and resources to ensure they are realistic before a single line of code is written. An unvalidated estimate is not a project plan. It is a mathematical hypothesis that ignores human volatility, leaving a project highly vulnerable to financial and scheduling failure. Before we can validate a projection, we have to identify exactly what corrupts the standard models. We can isolate 7 specific variables that consistently derail initial project estimates. First is incomplete requirements. A client requests a basic online storefront, but conceals the need for an AI recommendation engine and multi-language support until development is already underway. This diagram illustrates the second variable, scope creep. What begins as a simple online payment module expands mid-development into a requirement for credit cards and digital wallets, forcefully pushing the project into a higher cost and effort bracket. Third is a lack of management experience. Junior managers routinely calculate the time needed to write code, but fail to allocate hours for invisible tasks like database migration or security testing. Fourth is incorrect size estimation. Estimation models cascade. If the initial count of lines of code or function points is inaccurate, the error compounds through every subsequent calculation for time and cost. Fifth is ignoring operational risks. Projections that assume 0 server failures, 0 technology shifts, and 0 employee resignations will break upon first contact with reality. Sixth is the friction of new technology. Forcing a team to adopt unfamiliar languages creates an immediate severe drop in expected productivity. Finally, unrealistic deadlines. Management pressure often forces engineers to promise mathematically impossible delivery dates simply to appease a client in the short term. Standard estimation formulas assume a frictionless vacuum. These 7 error sources represent the chaos of reality. Validation is the mechanism we use to filter that chaos out. To correct raw data, we apply a multi-step validation function that tests the baseline estimate against empirical reality. Method 1 is expert review. Senior managers analyze the raw numbers and adjust the baseline assumptions using intuition gained from past project failures. This graph maps a data point from a past 60,000-line banking app to project the cost of a similar new build. This is historical comparison. Past performance data provides the most reliable metric for future execution. Method 3 applies multiple estimation methods. Instead of trusting a single formula, teams run the parameters through lines of code, function points, and Kokomo independently to find where the results overlap. Method 4 is prototype validation. Teams build a miniature, functional version of the software to establish a true effort baseline. Method 5 relies on team discussion. Incorporating cross-disciplinary input from testers, architects, and developers ensures blind spots in the timeline are identified before they become bottlenecks. Method 6 is formal risk analysis. Managers actively game plan potential project failures, assigning time and budget buffers for when things inevitably break. Validation is an overlapping matrix of filters. Each step is designed to systematically squeeze unrealistic optimism out of the project plan. This flowchart illustrates a dry run of the validation process applied to a hospital management system. The initial mathematically generated estimate predicts an 8-month development cycle. We pass that raw data into the expert review stage. Under scrutiny, senior developers trigger an alert. The initial projection entirely omitted the necessary security module, extended testing phases, and the database migration. The raw algorithmic calculation counted the visible features the client asked for, but completely missed the invisible structural backend tasks required to actually make the system function. Accounting for these missing variables, we process the corrected data through the revision stage. The validated project scope now outputs a realistic timeline of 10 months. An 8-month timeline is appealing on paper. It looks efficient. But a 10-month timeline reflects the actual work required. A validated estimate is often higher, and it is frequently harder to sell to management. But it provides the only accurate baseline that protects the company from critical failure midway through development. A thoroughly validated estimate exhibits specific traits. It is evidence-based, flexible to changing requirements, highly risk-aware, and above all, realistic. We can lock the sequential steps of this process into memory using the verify protocol seen here. V. Validate with experts. E. Estimate using multiple methods. R. Review requirements thoroughly. I. Identify hidden risks. F. Find historical data. And Y. Yield the final approved estimate. Bypassing this protocol leaves a project exposed to the crushing weight of reality. Budgets hemorrhage, teams burn out, and projects are canceled entirely. Notice that the I in verify requires us to identify risks. This points to the fundamental truth of software engineering. Uncertainty is a permanent fixture of development. Because uncertainty cannot be eliminated by math alone, project managers must actively plan for it. That requires moving beyond estimation and mastering the formal processes of risk management.